Hello, ME 326 students. Um, it's too bad that I have to send out a recording instead of being with you all. I hope you all are staying safe out there, and I hope that I can meet you in person next week. But anyways, let's get started today with our introduction to the class. So hello, this is ME 326 Intermediate Dynamics. My name is Tim Jane. I, although my name is Tim and I'm a graduate student, though, I would like it if you refer to me as Mr. Jane or Professor Jane. It's nothing about me being um, any better than you, but it's just a preference I have as being in a teaching role. Thank you. So yeah, let's get started here. So a little bit about me in my education and career. Um, I received my bachelor's in mechanical engineering with a concentration in mechatronics in March of 2022. I worked on a senior project, as you can see in the bottom left. I worked on the planarizer mechanism, which is essentially a robot, single degree of freedom um, leg testing mechanism. So you can see there's two carbon fiber booms that are attached to this leg. And basically the system allows for yaw and pitch for the leg. I've also passed the FE mechanical exam, um, and I am seeking professional engineering licensure eventually. That's one of those things that I highly recommend that you all pursue. Um, it's a great opportunity, um, even if you aren't seeking licensure, just to give you an edge up as you apply to jobs. Additionally, I'm seeking my master's in mechanical engineering, which is a program I'm in now, with the graduation date expected of June 2023. I've been a teaching assistant since spring of 2022 for intermediate dynamics, and I'm working on a thesis project. As you can see in the bottom center picture here, this is a mobile implant for a total ankle replacement implant. Um, so total ankle replacement, or TAR, is a less common surgery out there, as opposed to TKR, total knee replacement, THR, total hip replacement. But essentially, as you can see, the implant is broken up into three components: a tibial plate, mobile bearing, and talar component. So I'm performing a finite element analysis on an implant that incorporates a mobile bearing, and then there's also, which mobile bearing means that there's two articulating surfaces between the tibia and the talus, but there's also a fixed bearing, which is a rigidly attached bearing to the tibial plate, which I'm running analysis. So I'm running a comparison study between a mobile and fixed bearing implants. Within finite element analysis using software such as Abacus. Um, I'm also the project manager of the ride engineering competition in Slow Cape, which is a Cal Poly Amusement Park Engineers and Designers Club. So in the bottom right, that roller coaster model is a little project I worked on over break, which is to scale with the competition specs. That's a Superman themed roller coaster, if you will, the blue and red colors. Took steel, bent it, MIG welded it myself, and tube bended with conduit bender and stuff. But anyways, I'm working with a group of 40 students and managing them. Um, and because one of my career ambitions is to become in part of the theme park industry design of attractions. Disney Imagineers is one of my uh, uh, dream jobs, if you will. I'm also considering a community college engineering education or now university education route, where I can effectively, um, work full time as an instructor and eventually a professor, as eventually I will be pursuing my PhD. And I also hope to go into some engineering consulting. I really like design work. So, and the nice thing about consulting is you can apply like your any sort of discipline, whether that's dynamics or design or fluids, thermo, whichever route you want to go. Because consulting, you can get a large variety of tasks given to you at a certain time. Some of my passions outside of school, um, first I would say is my faith in God, and just that is something that's kept me grounded, give me a purpose, and yeah, just been really beneficial. Um, yeah, also being able to meet fellow-minded and people of different faiths too. It's a cool opportunity being a part of a church as well and stuff. I'm also passionate about music. So I play saxophone and guitar. Saxophone is my primary instrument as a part of the Mustang marching band. So that top right corner is me in uniform. And I also enjoy jazz and being a part of jazz ensembles as well. As far as outdoors, I also, I love world traveling. I went on a solo backpacking trip over the summer for 2 months where I visited 8 different countries. And as you can see, there's a couple pictures from Switzerland of me hiking around in this green, lush mountain country. It's astounding. Um, and yeah, I just love being out in the outdoors, and it's just it really it's probably being outdoors is probably my favorite stress outlet. Um, so I recommend that you guys find one over the course of the quarter. Just whether that's lifting weights or going outdoors, do something for yourself to take care of your mental health. Um, and um, and yeah, just don't be a stranger. Also, reach out. Anyways, about the class, we're going to be solving dynamic systems by decoupling differential equations with the state space representation, which is something that I will be going on over in lecture shortly. We're going to be utilizing um, vector loop kinematics to solve complex engineering systems with the kinematics and kinetics dependency. So motion and forces. And in order to analyze these systems, we're going to be using MATLAB and Simulink for both of these. So make sure you have those installed. And if you don't, please reach out because we do have computers available for use in the class, in the lab. Um, just let me know if you need a laptop, and we can be happy to provide this to you during activity time. Anyways, how do you succeed in this class? First and foremost, I would say ask questions early and often. That is something that's very important to succeed. Cannot stress that enough. Do not be a stranger. Um, Ask, even if you think it's a dumb question, it's probably not. Um, I bet you one other student is thinking that. So please ask. Um, the emails is a good resource, but really I cannot stress this enough. Office hours is the best way to receive help in this class and succeed. Um, my office hours and the other instructor, Wyatt, Mr. Connor, his are to be determined. I sent out a survey to you all. for completing that based on your availability. Please get that in as soon as possible. I'll also be sending that out as an email. Within office hours, I'm expecting a minimum working example of your code. So meaning that you should have put in some effort towards setting up the constraints like initial conditions and variable definitions and different things, function definitions. Um, that way we can troubleshoot, oh, like it's throwing a singularity issue or something. And we can work through that. Do not come with just a blank slate. Work with peers. I encourage you to work with peers. Collaboration is very important in the professional engineering environment. And I encourage you to develop that skill to collaborate with others. However, you cannot copy and paste your neighbor's code. That cannot be stressed enough. And also, you cannot ask ChatGPT to perform your code. I know that's a new development out there. And there are ways that we can find out if you've been using that or if you've been copying. So don't even try it. It's not worth it. You're cheating yourself. Um, you're here to learn, really. So keep that in mind. Late policy for the quarter. There will be no late assignments accepted for full credit. The maximum possible score will reduce 1% per hour, max reduction 50%. So with that being said, don't fall behind if you're stuck on an assignment. If you're stuck on one lab, like lab one, and we're already on lab two, just move on. Make sure that you don't fall behind. Just basically like keep up with lab two, and then come back to lab one once you're in a good spot with lab two. Would be my suggestion. And as far as the term project, there should be no latest submissions without my consent. In the past, I have granted extensions for extenuating circumstances, so I'm pretty reasonable with regards to that. So you can know that I do take your life events and am gracious in that regard into consideration. So course outline here. Yeah, so the first week we're going to be going over introduction to numerical analysis. So this week, next week we'll be going over Euler solver, simple pendulum, then a massless bumper simulation, and then analyzing a quarter of a car, a suspension, piston crank mechanism after that. Week 5, that should be week 5 and 6. I'm sorry, I forgot to edit this slide. And then our term project is not going to be the bike mechanics simulation. That was from last quarter. It's going to be the walking arm trebuchet, which is a very unique type of trebuchet. Look it up if you get a chance. It's got 3 major linkages that all rotate about each other. It's pretty cool, and you'll develop an animation of it as well to show off. But anyways, I think that's it with regards to the intro. I don't want to take up too much of your time with this video, so let's move on to our notes here. So I'm going to talk about what numerical solvers are. So let me just make sure that I'm screen sharing. Okay. Share. Okay. So numerical analysis, really the goal of this class goal is to solve higher order ODEs and linear systems with dynamic applications. So what's an example of a mechanical system that you can think of that would have differential equations? If we were in person, I would ask who's taken mechanical vibrations or who's taken um, system dynamics, because those classes have introduced you to um, a certain type of system. One system, which is the most common mechanical dynamic system that yields a second order differential equation, is the mass spring damper. So with the mass spring damper, obviously you have a mass, and then you have the spring, and then you have the damper. Can imagine those are ground connected, and you're supplying a input force, F of T. Now, if we remind ourselves, we can draw an FBD. So FBD is, so we have the spring force, F sub K, F sub B, and for the damper, and force. And the coordinates, this is only a one-dimensional problem, so the coordinates are drawn as such. Just positive x going to the right. Then on the MAD portion of it, mass acceleration diagram, we have mx double dot. Now, recall d dt of x is equal to x dot d squared dt, or the double derivative of x. So x double dot. The dots are time derivatives. Again, so now that we have our FBD and MAD, we can start forming our set of equations from Newton's second law. So Euler's law, we have some of the forces in the x, mx double dot. So we have our damper force minus Fb, our spring force minus Fk plus F of t equals mx double dot. Now our damper force is minus b times x dot, where b is the damping constant. Our spring force is minus kx, where k is our spring constant. X dot represents velocity and x represents position. Now we can put this in a form where mx double dot plus bx dot plus kx equals f of t. And then x double dot equal to negative b over m x dot minus k over m x plus 1 over m f of t. Now, solving for this by hand analytically is pretty tedious. There are certain ways to solve differential equations analytically. You can solve analytically using the method of undetermined coefficients. This is stuff you should have learned in linear 2 or linear 1. or Laplace. But there is a way we can make this simpler, and this involves the use of code. This representation, how do you think we can make this simpler? Well, it turns out that we can subdivide this second order ODE into two first order ODEs. And this process is called state space representation. State space representation is as follows. So we can introduce n number of intermediate variables called state variables. State variables are what you want from your system, are the variables of interest. So these variables of interest can be applied to a differential equation. So an ODE of order n can be expressed as a system of n first order ODEs. In our case, n equals 2 for a second order ordinary differential equation. This concept is very important for you to understand. This is the groundwork of the class. Please read appendices A and B. Excuse me. This will be very important for you to read through those. And please come downstairs for help. So, with that being said, let's apply this. Let's look at how to write a state vector. So, a state vector is typically denoted by x bar. You'll notice a state vector is typically the convention is to call the variable name x. And we have x and x dot collected within the state vector. So this is x bar of 1, and this is x bar of 2. And this is a column vector. And this is the state vector. State vector is what we want from the system. So we want position and velocity. But so we have position, we have an equation for acceleration, right? That's x double dot from the EOM, equation of motion. But how do we get x and x dot, position and velocity, respectively? Now this, remember in the analytical, we would have used the method of undetermined coefficients or Laplace to get us backtrack from x double dot from an EOM to get displacement. But in this case, we don't have that. We don't want to do that because that's just more tedious, more work than we need to. So let's look back at our example. Now, we're going to take the derivative because we only have position and velocity. We need to take the derivative of the state vector. So this derivative of the state vector equals d dt of x bar is equal to x dot and x double dot. Now, here, let me rewrite this. So the derivative of x, since we don't have an expression for x, we're just going to call it x dot. And that may seem redundant, but this is just the convention that we're going to use. The derivative of x dot, though, we have. That's from our equation of motion. And recall that was negative b over m x dot minus k over m x plus 1 over m f of t. With regards to MATLAB, you don't want to create variables for x dot and x double dot. You just want to reference the state vector. Reference based off the state vector. Do not create discrete variables for x dot and x double dot. So this really is going to be of x of 1, right? So that's the first position in the state vector. And then x bar of 2. So this is going to be x of 2, right? And then minus b over m, x of 2 minus k over m, x of 1 plus 1 over m f of t, which is the input to the system, like a forcing function, essentially, that's causing the vibration. Now this here is what you need to put into a function script. Okay, so I believe we have all of our bases covered and what we need to write down on paper with regards to this system. So now we can transition to MATLAB. And we're going to put this ODE function into it. So let's change my share. So the first thing we're going to do is put that state vector derivative into a function file. So we're going to do in MATLAB uh, under new, you're going to go into your live function. Okay. So my policy with function files is that you need to have like a header here. So you can change the header by putting a title. You can call this ODE fun. Give me one second here. So you need to give an explanation of the function and what it does, and then function the output. So, oh, I almost forgot. I need to describe why we're doing the state vector. So let's go back to the screen. So, okay, let's see. Okay, so if you recall, there's a numerical solver called Euler's method. This is going to be talked about next lab as well. So Euler's method says basically this is the state vector is equal to x of k at the next state, and x of k is the current state, plus dxk dt times delta t. So this is the state vector derivative. Which is essentially causing the change times delta t, which is the time step. From k to k plus 1. This is a fixed time step. So this is essentially what ODE 45 does is, or I'm going to go over that, you keep this in the back of your brain for now, okay? This state vector derivative is what is key towards this. Okay, now we're going to actually get into math. Okay, so within the function, we're going to call this x dot for state vector derivative. Now you need to call this a name of a function, so we're going to call it ODE fun. And when you save it, you have to save it as the same name as the function. So time is going to be an input, x, which represents the state vector. Not think in this class that x represents multiple things. it's a vector, so it has multiple elements. It's not just one scalar value. Tx mbk. By putting mbk, the constants, we have to define them in the main script, which I'll get to later. So x dot is equal to, and now we have to create a 2x1 column vector because this instantaneously, like I said with the Euler solver, it instantaneously solves for x dot. So x of 2 space minus b over m times x of 1, x of 2 minus k over m times x of 1 plus 100 times that's f of t, by the way, is e to the negative 3t. Okay. So this should be sufficient towards solving. This is for our example, but it's practically the same for the lab assignment. Then you want to do file new live script. The purposes of live script is really to, for documentation purposes, it makes it really easy where you can put text and you can put code in the same file. So an easy way I can create a header or the title is put the two percent signs and then say lab 1 introduction to numerical analysis spacebar. And then I can create subheadings by doing the same thing. Okay, so let's go back to the lab manual. Let's go to the lab manual for a second. So in the assignment, your differential equation is given as such. So you can imagine, see how it's a d squared q dt squared? That's like x double dot, except it's q double dot in this case. So this is the mass. This is m is 2, b is 10, is equal to 10, and k is equal to 12. So the mass, the damping constant, and the spring. And the forcing function f of t is e to the negative 3t. Now we have initial conditions given as 2 and 1. So you're going to want to read this thoroughly. This is a function file template I essentially did for you. And I added m, b, and k because I didn't want to define it in the function file. But if you don't add m, b, and k, you have to define them in the function file here. Okay. So now our deliverables here is to plot the input forcing function and the response, the displacement, Q of t against time. So actually these, think of it this way. So you should be plotting the results from MATLAB, which I'll show you that method soon. But you also have to find an analytically, you have to use the method of undetermined coefficients or Laplace method to solve that differential equation for Q of t, and then to derive it to get Q dot of t. And you'll get the C1 and C2 values to constants by doing that. I'd be happy to check those with you as you work through them. And then you're going to compare them with the MATLAB and Simulink. So I'm going to go over those methods here first. So with regards to the analytical, so the analytical is the first portion. This isn't the format you want to follow. I'm just doing this for a teaching perspective. I'm just going to break it up into analytical and numerical in terms of divide, but really you're going to want to follow the report format, and we're going to it's expected that you read through that thoroughly and that your reports are conducive to that format. So the analytical here, so you're going to define first, you're going to define T. So T is equal to lin space. You can do a lin space, you can do whatever you want. So with the way lin space works is 0, the starting point, 4 is the end point, and then 100. I mean, that's the number of points. Make it 1,000 if we want. Then you want to define what C1 is equal to and C2 is equal to from your analytical study. And each line should be, I expect copious commenting. So comment every variable to indicate what it is. Q sub of A, QD sub of A. So that's his, right, the analytical displacement. And then you're going to want to plot those responses. So you're going to have figure, and the first one for deliverable ones, expecting subplots, the way you create subplots is subplot. And then you specify the number of rows within the grid. So we have 2 rows and we have 1 column. And then we want the position to put the subplot in. So we're going to say plot. Anyways, there's a plot function. You're going to need to use the title function, the X label function, the Y label function, things like this. But anyways, don't get confused. This analytical portion, in deliverable 1, I'm expecting the numerical results for subplot 2. But this is needed. Analytical is expected for deliverable 1, deliverable 2. And then, okay, so let's get into state space numerical solver. ODE 45 is a differential equation solver. Okay, so first we need to define our initial conditions. So 2, 1. You can create a 2x1 comment or column vector by just putting the semicolon. So this is state vector initial condition. Then we want to define this a span of times that the differential equation solver is going to work through. So you only want to do a row vector of 2 elements, 0, 4, and then define M, B, and K. And then this is a tricky portion of the class. So recall anonymous functions. So an anonymous function was something where we had y is equal to at t and then t squared. So I want to make a very clear distinction here that the y on the left-hand side of the equation, that's called a function handle. That's a container that stores the function that's actually being performed. That's all that is. It's just like a variable. It's a container. It's a storage element. The at and then parentheses is the input variable that we want to pass into this function. So in this case, t. And then t squared. We're taking the square of it. So with that being said, we want to do the same thing, but create an ODE handle. So it's going to be called ODE handle. And then at, we have to have our variables in the at portion. So the input variables to pass through for the simulation, the input variables to pass through the anonymous function. So those are going to be at t comma x. And then ODE fun, that's the name of our file, right? So is you have to have your function file and your main script within the same directory. So first of all, I'm going to save these files. So ODE fun. Okay, I'm going to create a new folder. That's an old example folder. We'll create an example 01 just for today's date. ODE fun.mlx, right? Because that's what the function name is. This one is going to be called lab1 main. Okay, this here, pay attention to this. You have to make sure that, okay, suppose that I was working off of, okay, I'm just doing random stuff, but I'm going to show you this, okay? Look, this live editor, see this blue tab? This is the folder that the file is in right now. So remember, we put in this example folder. So look what happens when I run it. Okay, so essentially, well, first of all, let's apply dummy values to this. And let's comment this out to them. So these are dummy values. Do not use these values. But essentially, what I'm getting at is you need to be in the same folder. Otherwise, it's going to throw errors. So the way you do that is this. At the very top bar here, this tells you the directory that it's like thinks it's in, or like the directory that the MATLAB workspace is working off of. And you're working on a file in a different folder. So to change that, you click on this with the green arrow coming out of it, and then click on lab one example. So it has to be that same folder, example 109. Okay, now you're good because it knows where ODE 45 is. Okay. So with our function handle, so we have the function, which last time the function for that simple anonymous function was t squared. Well, now we're working off of an actual external function within the context of an anonymous function. So this is sort of a confusing topic, so don't worry if you don't get it just yet. So see how in that dialog box, it gives you the input variables that you need. So you need to enter values in for those, or you can just, if you have them all assigned, you can pass those in. Okay. So see how I changed that? So you're probably thinking, wait, we haven't defined T or X. So how is this going to work? So that's essentially what we're sort of doing in the next line. And we're using the Euler's method to do this within ODE 45. Because ODE 45 is Euler's method, an extension of Euler's method. We're gonna, so you first you put your function handle. This is the function handle, T span, and the initial conditions vector. So see, you're getting data now. That's good. That's what we want. So if you're getting data where it says X out is equal to 49 by 2, that's good. So now that we have data, we can put these into containers or variables. So position is equal to X out 1. So what I just did is I said, take all the rows of X out. So see, I'm going to take every single row, but just give me the first column. That's what the second element is. Velocity is equal to X out 2. Second column, all the rows. So the second column, so that's exactly what we want. Because, see, let me explain how this works. So, and sorry if I'm being redundant, but this is just, I really want to hammer this concept down because this is the basis of everything we do in this class. So remember that we found dx dt with regards to the state vector. So dx bar dt and then x bar is the current state. So x bar of 0 or x 0 is equal to 2 and 1. So we want to find x bar of 1 plus dx 0 dt times delta t. So essentially what we're going to do is within that function file. So you know how we had, so for this step, I'm just looking at the first step, okay? So this is going to take x naught of 2, and this is going to be minus b over m times x naught of 2 minus k over n times x naught of 1 plus 1 over n x, right? Something like that. So, eventually, so that's the solve for x dot naught. So like I could literally repeat this process um, for x naught of x dot of 1, right? Because this is an instantaneous process that just keeps iterating through different steps. So I hope now that you can see that that works because it's an extension of Euler's solver. So ODE 45 takes care of that for us. Next week you're actually going to be hard coding Euler's method into it and comparing that to Euler's solver. Okay. I know I've taken a lot of your time here, so I apologize for that. But we do have to cover the last thing, and that is Simulink. So this is what your model should look like. I'm just going to be going through the process here. So the first thing you want to do, input a time block. The way you input blocks in is you double click in the space and you can search the blocks. So we're going to do time or clock block, sorry. Decimation corresponds to how long we want to run the system. So we can change this to 4, stop time, 4. Then the next thing we need to do, so this is time, the signal, so you can drag this out. So if you double spacebar, it zooms in. And then we have to input this thing called the math function block. So MTH. So that's going to take E2. Oh, before we do that, we need to put a gain block. So this is just a constant block. This approach is called the block diagram approach. So if you've taken 322 system dynamics, you'd be familiar with this process. Um, so you're going to have a gain -3. And then now we put the math function in. Yep, so we want to make sure that's on the exponent. Okay, next thing we need to do is put in an x. So that's the forcing function now. You want to make sure you label every single signal. See how as you move across the line in a block diagram, it gets multiplied. So t got multiplied by -3 to give you -3t, and that getting multiplied. This is what u is, which is getting inputted to this block. Okay, so the next thing we need to do is put in the sum block, which is a summing junction. So we need to do minus, plus, minus. So this function, so we're going to be basing this off of um, this equation here, x double dot equation. So that's why I have that as positive. So this signal is x. We have to label every single signal you do here. So now we have to integrate acceleration, right, to get velocity. So you could use this integrator block. See that? So you want to get the second part of that because that second element of that initial condition corresponds to the initial velocity. Okay, that's the initial position. So remember we had a gain for x dot. Um, so we need to satisfy that equation that I wrote down. So remember this is why I have the negative because we need to multiply it by b over m. So I'm gonna have to create a pickoff point. And the way you do that is you right click on the signal that you want to create a pickoff point from, and you drag it. So now I have to put that gain block. And then the way you flip gains, format, um, you say, yeah, flip block or control I. And typically gain blocks, you want to make sure that they're positive. The next thing we have to do is we actually have to do this thing called a two workspace block. So you double click on it. Please remember this. You need to change the save format from time series to array. You must do this on every single two workspace block, otherwise it will format it strangely. So you will change it to array and press OK. And we're going to change the name to velocity. And then so now for workspace position array, and we feed this back. Gain, control I, K over N. Okay. And there you have it. That's your fully developed um, Simulink file that you'll need. So let's save this lab one model dot. Oh, wait. Okay. You're gonna want to call it lab one model since I have my existing one called lab one model. I'm just gonna call this lab one example. Okay, cool. So now we're gonna look into sim out. and we can use all these velocities variables now. So you can call it like pause sim simulink equals sim out dot position and so on. Okay. Um, see, the last thing I need to talk about, I'm just going to go over report format again, just really quickly. So, so you want to give a description, the required files that were used in this, table of contents, uh, problem statement, what you're doing in this lab, analysis like hand calcs that you do in the lab, constants, all these different things. See how generously or thoroughly it's written in text. So you're going to want to be sure to do that. And then you want to append your function file to the end of all the reports. With regards to reports, I would so you can in the live editor you can export. So first off, you're going to want to export it to Word. And then in Word, you want to format it so it doesn't create weird page breaks and it's nice. And then you save it as a PDF and turn it in. So yeah, that's all I have for today. Um, thanks for hanging with me there. And yeah, I hope to see you next week. Yeah, have a good one.